Welcome back. In this section, we're now going to take everything that we've learned in the first part of Chapter 3 and apply it to sketching a graph of a function. Of course, we're not going to forget all of the things that we've learned in pre-calculus, so we'll still use what we know from pre-calc to help us out, which means that when I start looking at any function, of course, I'm going to think about its domain. I'm also going to, if I can, find intercepts. I say find x-intercepts if possible. Maybe the function is particularly nasty, in which case, maybe we're not able to do so. But if I can, I should, and if I can, plot those points. I may also know from pre-calculus whether or not I've got a vertical asymptote. So for things like rational functions or things involving trig functions like tangents or secants, I'll know that there should be some vertical asymptotes popping up, and I should know where those are. I might also have, if it's a rational function, a hole showing up on the graph. If I have that, I'll figure out its coordinates and I'll plot that point. But now the big thing that we'll be able to do is now apply all of the calculus side of things. So first off, we'll be able to find via calculus horizontal asymptotes or oblique asymptotes, and that was what we did back in 3.5. So all of those limits as x approaches infinity or negative infinity. I know some of you are probably thinking, well, we did horizontal asymptotes in pre-calculus, and that is true. However, that was really only for rational functions. There's lots of other functions out there that we wouldn't be able to analyze with just pre-calculus tools to figure out their asymptotes. So we might have some functions where maybe we can rely on our pre-calculus knowledge, but there might be some ones that are requiring us to actually use limits at infinity. The next thing we should probably do is think about where we're increasing and decreasing, figuring out where we have maxes and mins. All of this is basically section 3.3 when we're finding our critical numbers, finding the first derivative, deciding where we're increasing or decreasing. And then, of course, once we know where we're increasing or decreasing, we can also decide which critical numbers happen to be relative extrema. As we find all of those, we'll always be going back and finding the x and y coordinates for all those points, because when I find my critical numbers, they may be places I'll need to graph, so I'll need to know y coordinates as well. And then once we know all the maxes and mins, then we'll work on figuring out how concavity is working. And so we'll look at our second derivative, and we'll find out where the second derivative is 0 or undefined. We'll do our usual number line business that we did back in 3.4 to figure out where we're concave up or concave down. Of course, if there's places where we switch concavity, we should be able to tell whether or not that counts as an inflection point. So if it's a place where our function is defined and where we have some sort of a tangent line, and if our second derivative is changing from concave up to concave down or vice versa, then we've got ourselves a point of inflection. And then once we have all those information, all the stuff from calculus and pre-calculus, then we'll put everything all together and figure out what our graph looks like. The same advice I would have given in pre-calculus I'll give here as well, which is that your clues should not contradict each other. So, for example, suppose you knew that at x equals 1 you had some sort of relative minimum. Then you know for sure you should be concave upwards. If you had a relative maximum, on the other hand, at 1, if that's what you thought you had, and you also thought you were concave upwards, you couldn't be able to do both at the same time. Having a maximum would mean you're concave down, and being concave upwards precludes you from having a maximum. So that means that we should think about, if we arrive at any point where there seems to be a contradiction in our clues, that we should go back and investigate what we did, and there's probably a mistake in the mathematics somewhere along the way. Okay, I'm going to look at this first one where I didn't even really give us a function. I just wanted to give us basically all of the clues, and then for us to figure out what's going on for this graph, and then to start plotting things. So firstly, as we're looking at the real functions later on, we'll probably start making notes of things as we go as to who is a max and who is a min. or who's a point of inflection. Here it's basically all of our clues all jumbled together, and so it might be a little bit tougher for this one to figure out exactly what's going on. So first things first, we know that our function is continuous everywhere, so there's no asymptotes, there's no holes. We should be able to draw this curve with one smooth line. That should be nice. The other thing that we know here is we're told in terms of limits that as x goes to negative infinity, the limit is 0, and same thing as x goes to infinity. So that's, in other words, telling us that we're going to have a horizontal asymptote y equals 0 on both sides. Of course, I have to remind myself when I say on both sides, because for every function out there, maybe it might have a horizontal asymptote on one side or only on the other, or it might have a different one on the one side versus the other. So we can't just take it for granted that when we have a horizontal asymptote, it's always going to be the same on both sides. But for this one, it says it is. So on both sides, we have that. And then in our little table that we've got here, this first column, be careful, we have either x-coordinates being given or intervals. So when we see something like this, negative 4 minus 2, that is not a point that's on our graph. That would be an interval of x values going from negative 4 to negative 2. So if we're talking about actual points, points would happen when you have an x-coordinate and a y-coordinate, and the y-coordinates come from f of x. So in other words, I have a couple of points that are given to me. I'm told, for example, that when x is negative 4, the y value is negative 1, or similarly, when x is negative 2, y is negative 4. I've also got the points 0, 0, 2, 4, and 4, 1. Those are all points that have been given to me, and maybe that might be a good first move for me to do, is just to start putting those points on my graph. So I'll do that right now, and then we'll go back and we'll think about what the other clues have to tell us. So we had 4, 1, there was a 2, 4, 0, 0, there was the minus 2, minus 4, and there was a minus 4, minus 1. I'm going to come back and label all these points afterwards. I just wanted to plot what I have for now, and then we'll go back and think about what else we know from the function. So the first thing that we know as far as the graph goes, we're told things about what its first derivative is doing, and we know for a lot of the intervals it's negative. In other words, we're decreasing. So if I'm thinking about this graph all the way up to negative 4, we're decreasing, and then from negative 4 to 2, we're decreasing some more. I'm also told here that at this point, at negative 2, negative 4, my first derivative is 0. So in other words, I have a critical number at x equals negative 2. That also happens later on. At positive 2, you can see I also have a second derivative of 0. So I have a second critical number. So two places where maybe I might have a maximum or a minimum. I know that at that point, it says my second derivative is positive. So where I have a critical number, I have a positive second derivative. In other words, we're concave up. That means that that point, negative 2, 4, should be some sort of minimum value. Similarly, I can say that at 2, 4, at that point where I've got my critical number, it has this negative second derivative, and if you have a negative second derivative, you're concave down, which means at 2, 4, we should have a maximum. So I'm just going to go back to my graph now and just sort of curve that in, that there should be a minimum at negative 2, 4, and there should be a maximum at 2, 4. So maximum at 2, 4, minimum at negative 2, negative 4. And that seems to be matching up with what I think the graph looks like it's going to be doing. Let's start thinking about the other stuff that we've already mentioned. So firstly, we already mentioned that as we're getting to that minimum value, we were decreasing and then we were decreasing some more. So if I'm thinking about my graph, decreasing and decreasing some more, that matches. If we're thinking about concavity, we also know that we're concave down all the way till -4, and then we become concave up after -4. And at -4, that's where we're switching concavity. In other words, we happen to have a point of inflection at -4, 0. So let's draw that in. Concave down, switching to concave up. So concave down, switching to concave up. I'm going to make that look a little bit smoother. I'm also going to put in here, now that I'm thinking about doing that, the horizontal asymptote y=0, because now I can finish off the left side of my graph completely. I know that we're becoming horizontal to the line y=0, and so there we go. That accomplishes the first part of my function, decreasing followed by decreasing, where we're concave down, then concave up. And now let's fill in the rest. Going from the minimum value onwards to 0, 0, at that point we're increasing and concave up. So I should be increasing and concave up until I get to 0, 0. And now let's see what happens at 0, 0. At 0, 0, our second derivative is 0. Before it, we had a second derivative that was positive, concave up. So after it, we have a second derivative that's negative, concave down. So it looks like we have another point of inflection. We're going to be still increasing, but we will be concave down for the next interval. So increasing and concave down, which matches with what we were expecting to see. We've got a max at 2, 4. And then finally, leaving that maximum at 2, 4 and heading to the end, we can see what's going to happen. After we leave 2, 4, we are going to be decreasing, followed by some more decreasing. Between 2 and 4, we'll be decreasing and concave down. And after 4, we'll be decreasing and concave up. Again, we're changing concavity, so this other point, 4, 1, is another point of inflection. So let's graph that in, where we are going to be decreasing and concave down, and then decreasing and concave up. And I also noted that we had a horizontal asymptote y=0 on both sides. So we'll become concave up, decreasing, and becoming horizontal to the line y=0. And now all I need to do is just label my points. And I only had those ones to label. There we go. I've labeled everybody else. I've labeled my horizontal asymptote. So now I can say that this should be a graph of what f of x looks like. Based on all of the clues that we found, this is what our function should look like. Okay, so we'll start with just doing a quick and easy first one to get our feet wet, graphing a nice little polynomial function, and then we'll work on to some messier ones after that. So for our first one, a nice polynomial function, and I know since it's a polynomial, there's lots of things I can say. Number one, the domain is everything. I also know polynomials never have vertical asymptotes, and they never have horizontal asymptotes, so I don't need to really worry about that happening. If I wanted to think about x-intercepts, that's easy enough to spot, because for x-intercepts, I would just be looking for where that function is equal to 0. And if I were to look at that, I would see that there's two places where x is equal to 0. Two places where the function is equal to 0. One of them is at 0, and then the other one is at 3/2. So we have two x-intercepts. The other thing we'll also notice that that's the point 0, 0, which means that that's also the y-intercept. So actually we found x-intercepts and y-intercepts all at the same time. So now let's do the calculus side of things. So this was all the pre-calc. We had a domain of everything, no asymptotes or holes to worry about. We've got a couple of intercepts. And now for the calculus side, if we're looking for the first derivative, we'll find that it's 18x squared minus 18x. And that, of course, that derivative is defined everywhere. And if we're looking for where is it equal to 0, we'd find that it's equal to 0 at exactly two places, at 0 and also at 1. So that means we need to go ahead and draw ourselves a little number line and figure out what happens to our derivative on either side of all of those numbers. So what happens when we're less than 0, between 0 and 1, and greater than 1, so we can tell if we're increasing or decreasing or what's going on. So if I were looking at negative 1, I would find for my derivative that f of negative 1 turns out to be a nice positive number, which means we're increasing. And if I evaluated my derivative at a half, I get a negative number, so I'm decreasing. So I know already one thing is for sure, that I happen to have a relative maximum at x equals 0. I know that because I increased and followed by decreasing, and 0, 0 is definitely a point in my domain, so we could have a max there, and indeed we do. So I'll make a little note to myself that we have a max at 0, 0. And now if I look at bigger than 1, if I were looking at, let's say, positive 2, and looked at what happens to my derivative, I'd get positive 36, which means we're increasing. So that means we also have a minimum now. I know that I decrease to 1 and followed by increasing afterwards. And so I have a minimum at x is equal to 1. We might need to take a little moment on the side to remind ourselves of what the y values are. So for our first critical number, we already knew when x was 0, y was 0. For the second point, we need to go back and figure out what our y value is. And so for that, we go back to our original function and put in 1. And our point is 1, negative 3. So actually, I've got 2 points that I can now graph on my function, so I should probably do that. I'll plot 0, 0, and I'll plot 1, negative 3. I also know, and I said this, that 0, 0 was going to be the location of a relative maximum, so maybe I'll just draw a little curve like that there, and 1, negative 3 rather, is supposed to be a minimum, so I'll draw a little curve there as well. For sure, these things are going to connect, but I mean, it's pretty clear that there's probably going to have to be some sort of point of inflection in between somewhere, because we're changing from concave down to concave up. So I'm not going to connect these curves just yet. I still need to figure out what have we got going on as far as concavity. So I guess next thing that I'll do is I'll figure out my second derivative. And for that one, second derivative turns out to just be 36x minus 18. And for that one, we can find that the second derivative is only ever equal to 0 when x is equal to 1/2. And so if we do the same sort of number line business, this time using our second derivative, I can find that at 0, our second derivative turns out to be negative. So we are concave downward in that first interval. And then after 1/2, so if I picked a value of x being 1 and put that into my second derivative, I get positive 18, which is indicating concave up. So we definitely have the x equals 1/2 as a point on our graph for sure. And in fact, we can figure out for that point y equals f of a half, which turns out to be negative 3/2. There we go. So in fact, we can figure out that this is a point of inflection. It's a point of inflection because it's a point on our graph where our function is defined. There is definitely going to be a tangent line there because the derivative is certainly defined at that point. And we're also changing concavity from concave down to concave up. So now I'll plot my last point that I have there, the 1/2 negative 3/2. So I'll plot that on my graph. So 1/2 negative 3/2 should be somewhere over here. And now I'll have my graph to fill on in, and I can say, well, I'm going to be concave down until I get to that point of inflection, then concave up afterwards. I know that after my minimum, I was increasing all the way after x is equal to 1, and I know that I was going to be decreasing after x is equal to 0. I just realized there was one more thing I haven't put on my graph, and it was the thing that I said at the very beginning, which was my x-intercept, the x-intercept of 3/2. Just as I was drawing my line, I realized I was about to cross through the x-axis, and I should probably indicate where that is. So now we can figure out the real final drawing of our graph, leaving our minimum value, heading through that x-intercept and heading straight upwards and increasing forever. And after our last x-intercept at 0, heading downwards forever. So now just a little bit of labeling, and then we are finished, and I can feel pretty happy about the graph that I've got here. So I have 3/2 0, 1/2 negative 3/2, 1 negative 3, and 0, 0 was at the origin, so I don't have to label that. And so now I'll just label this with the equation 6x cubed minus 9x squared. And there we go. We've got a well-labeled, nicely sketched graph of this function.